Okay, welcome to my channel, and here we'll be discussing about we'll be discussing about fundamental and derived quantities. It's actually a topic under units of measurement. So, fundamental quantities are those quantities you can describe fundamental quantities as those basic quantities that are independent of others and cannot be defined in terms of other quantities or derived from them. The units of these fundamental quantities are called fundamental units. So the table that you see there on the screen are the basic fundamental quantities and their units and the abbreviations of their units. You can see that at length the unit is meter, the abbreviation is m. Mass, the unit is kilogram and the abbreviation is kg. You can as well see time, seconds, s. You can see amount of substance to be mole and the abbreviation is mol. That's mole too. The unit in there on your screen there, there's SI unit system. You can see the SI unit system. Those are the standard. Those are the standard units that are applied in making measurements. It is called the System International Units. The SI units are the principal systems of units used in scientific work today. Okay, having done that, let's briefly talk about derived units. So what are derived units? So you can derived units can be expressed as those units obtained by some simple combination of the fundamental units. So basically we measure length by the meter rule, of course, and the unit for that is length. These systems of units are very important when evaluating or finding out about the dimensions of physical quantities. So we will take a look at some we will take a look at dimensions of physical quantities and how to use these fundamental and derived units to derive dimensions of some basic physical quantities. So let's take a look at that. Okay, looking at dimensions in physics, dimension has a special meaning. It is actually the it actually denotes the physical nature of a quantity. The symbols that are used to specify the basic fundamental quantities like length, mass, and time are denoted as L, M, and T, as you see on the board, and is usually enclosed in square brackets like this. Now, knowing the dimensions of these parameters are very important, and it's actually used in dimension analysis to test if an equation is dimensionally correct. It's actually very useful in a lot of things, but here I will just show you how to derive dimensions for basic quantities in O-level physics like this. For example, let's derive the dimension for velocity. Example 1, let's look at velocity. So first of all, you ask yourself, what's the formula for velocity? Velocity is actually the rate of displacement, which is distance all over the time. So in dimension terms, you have this. Distance is measured in length, and its length, the dimension for length is L, and divided by time. So from your indices, you can write this as this. So that gives you the dimension of your velocity. So in the same vein, we can do for a concept like acceleration. So acceleration is what? Acceleration, from your O-level physics, it is the time rate of change of velocity itself. So it's like the velocity divided by time. So what does that tell you? If you are taking the dimensions for the velocity, it will be this velocity all over the dimension of time. Of course, the dimension of velocity was given here to be Lt minus 1. So you fix it here. Divided by t is always for time. So using your indices is something like Lt minus 1 minus 1. You're actually subtracting the powers because you are dividing t minus raised to the power minus 1 divided by t is t raised to the power minus 1 minus 1. That will give you what? Lt minus 2. Okay, I think the camera is not showing and the downside. So that's what I mean. Lt minus 2, like Lt minus 1 divided by t gives you Lt minus 1 minus 1, because you're actually dividing following your laws of indices in basic mathematics. So that will give you Lt raised to the power minus 2. So having done that, our third example, we'll try to bring out the dimension for force. And what is force? Force is what? The product of what? Mass and acceleration. So if we know force to be the product of mass and acceleration, we know that to get the dimension, then our mass is always what? M. Okay, our mass is always M, and our acceleration, we found it out to be what? Lt minus 2. So the dimension for force will be mLt minus 2. Though you can still write this as mL over t squared. It's just your indices. The next parameter we would like to look at here is something like work. So we want to deduce the dimension for work. I know that work is what? The product of your force and your perpendicular distance. So you can describe work as the product of force and distance. We know that we can, the dimension for distance, distance is always length. Force, we find it to be mass times acceleration, which later gave us mlt minus 2. So work, the dimension for work will now be mlt minus 2 times L. So using your laws of indices, this will be m, you are multiplying L by L times t raised to the power minus 2. So from your laws of indices, you know this comes with a power here 1. This also comes with a power of 1. So this will give you m L1 plus 1. You also multiply it by t raised to the power minus 2. And that gives you m L squared t raised to the power minus 2. Having done that, let's check pressure. So what's the dimension of pressure? Now, if you want to look at the dimension of pressure, we will see that pressure can be defined as the force per unit area. That's what pressure is in physics. Pressure is a ratio of force and area. So what is area? What's the dimension of area? Area, we are used to solving area. It's always the multiplication of two lengths. For example, the area of a rectangle is length times breadth, which are two lengths, and the unit is always meters, which is L squared. So our dimension for area is L squared. Our dimension for force was given to be what? mlt minus 2. So pressure, which equals the force over area, will be mlt minus 2 all over L squared. So this is actually what you are dividing here, m L over L squared t minus 2. And of t minus 2. I know for the guys in O level, this can be a little bit challenging to do. This, but this is like saying, using your indices, this is like saying m L here comes to the power of 1. So it will be 1, you are dividing, so you are subtracting the powers, 1 minus 2, then t minus 2. So that will give you, that should give you m L minus 1 t minus 2. So you know it's also the same thing as writing m all over L t squared from your indices. Now, one of the importance of dimension is you can use it to check if an equation is actually correct, if an equation is actually dimensionally correct. So using our dimension analysis that we've just done now, you check if this basic equation of motion is actually correct. Equation like V equals to U plus AT. So this is one of your equations of motion. So this V, you know, is your final velocity. U is the initial velocity, A is the acceleration, and of course your T is also your time. So looking at that, we know that our velocity, the dimensions of velocity is what? The dimension for velocity is Lt minus 1. Acceleration is Lt minus 2. So you substitute that into this equation and see what you get. Now to check if the equation is dimensionally correct, that means the left hand side the dimensions of the left hand side should be the same as the dimension of the right hand side. They shouldn't be dissimilar. So our velocity for the left hand side will be Lt minus 1 equals to U is initial velocity, so it still takes our dimension for velocity, Lt minus 1, plus A is acceleration, it takes Lt minus 2. Now A is multiplied by T, and our T, time, is what? Capital T. So if we take that in, we have Lt minus 1 equals to Lt minus 1 plus, remember your loss of indices here. If you're multiplying T by T, it will give you have to add the powers. So minus 2 plus 1 will give you what? Minus 1. So this is Lt minus 1 plus Lt minus 1. So this will give you Lt minus 1 equals to 2 Lt minus 1. Now you are not concerned with 2 because 2 is a number and it's a constant. But what you are concerned with is this. You can see it's similar to this. So this equation is dimensionally correct. The equation is dimensionally correct. So thank you for watching. I hope you will join me in my next tutorial, still in O-level physics.